relating to the dynamics and variability of the Asian monsoon. He has done his PhD from Physical Research Laboratory, and he has publications more than 63 papers in international peer-reviewed journals and 17 research reports. He has won several awards such as Dr. Narasimha Rao Award from Anna University, 11th Silver Jubilee Award from Indian Institute of Tropical Meteorology, Frontier Outstanding Research Award, Professor A.D. Wernerker Award, IIT Madras Golden Jubilee Biennial Award, and he is the editor in Earth System Dynamics, which is open access journal. So now I invite Dr. R. Krishnan to start the session.
Good morning to all of you. So it's a pleasure to see Professor Ramesh, my co-convener, Dr. Ramesh Kumar, Dr. Sunil Singh, various esteemed and distinguished scientists, delegates, students. It's a great honor for me to present this talk and also act as a co-convener of this session. We have basically two presentations, myself and Professor Ramesh. So each one 45-minute slot, each of us will speak for 35 minutes and then we can have some discussions. So with this, I welcome you all to this session. And today, this being a session on climate change and monsoons, I thought this is a work that I'll be describing about some high-resolution climate change simulations of the South Asian monsoon in a warming environment. And these are all my co-authors who have contributed, both from India and France. Basically, what I will be showing is the monsoon precipitation over India in the last few decades has shown some interesting changes, some trends, long-term trends. So the question is whether this is naturally forced or is a part of a multi-decadal variability, or is climate change really affecting? This is the problem we wanted to understand. So this is the talk will focus on that. So this is more of a schematic for the general audience, showing the basic drivers of the monsoon circulation. You have the elevated Tibetan Plateau, which warms up during the pre-monsoon months. So you have a land-sea contrast between the land and the ocean, which sets up the monsoon circulation. But once the monsoon circulation is set up, the moist winds from the Indian Ocean blow towards the Indian landmass, and so they produce rainfall. So this rainfall also leads to a lot of latent heat release by the latent heat release of condensation, and the feedback between the latent heating and the circulation maintains the monsoon. This is a very simple schematic of the monsoon. And of course, there are year-to-year variations in the monsoon rainfall, which are driven both by internal dynamics of the monsoon system and external drivers like ENSO. So this is a very simple concept of the monsoon. And all India, we know that the rainfall during June to September, whole of India accumulated rainfall for the season mean is about 850 millimeters. And of course, there is spatially a lot of variation along the Western Ghats and Northeast India. These are regions of heaviest rainfalls. And over the eastern part of India, Indo-Gangetic Plain, number of synoptic systems like the lows and depressions, they give widespread rainfall. And areas over Northwest India are relatively much drier. And this is an index of rainfall from All India rainfall from IITM from 1871 to we have up to 2016 now. You can see that all these red bars are the years of deficient monsoon or so-called droughts, and all the green and the blue ones are the wet monsoons. So what you see, many of these red bars are associated with, you can see circles, they are all during El Nino events. So many of the droughts over India have occurred during El Ninos. And likewise, El Nino means a warm phase of the sea surface temperature anomaly in the central and eastern equatorial Pacific. So many droughts over India have happened during El Nino phases, whereas wet periods have accompanied during these cold phases known as La Nina, anomalously cold periods in the Eastern Pacific. But you will also see many years which are not associated with El Nino or La Nina. So there is a lot of internal variability in the system. But what is interesting is, in the second half of this full period, if you see, the number of droughts have significantly more in number, compared about 40% more compared to the first half. And so this is something interesting. And we also see that the rainfall has been experiencing a decreasing trend in the seasonal rainfall over India. So this is a spatial pattern of the rainfall from 51 to 2007, based on one of the data sites known as the Aphrodite, which also uses the IMD data. And all this blue color along the Western Ghats and along the Indo-Gangetic Plain, you can see that it has undergone a significant decreasing trend in the rainfall. Of course, there are some pockets where rainfall has also increased, but country as a whole, in the last 50 years, the rainfall has declined by about 6 to 7%. And this was a paper in Science by Professor Goswami. They had looked at the daily rainfall over central India, which is well correlated with rainfall over whole of India. What they find is the count of low and moderate rains, that is the intensity between 5 to 100 millimeter per day, those rainfall counts have decreased, whereas the very heavy rainfall events and the heavy more than 100 millimeter per day or 115 millimeter per day, those intense rainfall events, those occurrences have really increased significantly. So on the one hand, you have the monsoon rains, seasonal monsoon rains decreasing, the low and moderate ones decreasing, and whereas the heavy rainfall ones those events are increasing. And this is not a good news, because it can really affect the groundwater and the surface water storage, and because heavy events are going to increase the runoff. So this is not a good, healthy signal. So why is this? This is what we'll be examining in this thesis. So this this decreasing trend in the rainfall is also supported by weakening of the large-scale monsoon circulation, which we have. So these are what I have shown is the back trajectories. These are all these various points over India and South Asia. We do a 21-day back trajectory. This is done from May to September every year from 1958 to 2006. And so 21, we try to see where the air parcels are coming from. So you see a lot of particles basically coming from the Indian Ocean, that is the main source, and occasionally particles coming also from northern parts of the Asian continent. So we counted this type of trajectory year by year, and so we made a kind of density of flow reaching the Indian region. And this is a kind of climatological mean density of the flow pattern. You can see the maximum flow comes from the Indian Ocean, which is kind of well known. But what is interesting is, if you look at the density of the flow average over the Indian Ocean region, that flow has significantly declined. So basically what we try to interpret is the decreasing trends in the rainfall, monsoon rainfall, are basically reflected in the weakening of the circulation and the flow coming from the Indian Ocean. And the other interesting thing is, during summer monsoon time, there are a lot of the synoptic systems known as lows and depressions that form in the Bay of Bengal. Lows give a lot of widespread rainfall over central India. And these lows, they generally try to grow through instability mechanisms. They become depression and deep depression. And these depressions and lows, they go west-northwest, giving rainfall along the Indo-Gangetic Plain. Typically, there are about 10 to 12 depressions every year, climatologically. But in the last few decades, we see that there is a declining trend in the depressions. Basically, the lows are not really intensifying into depressions. And in fact, a year like 2010, there was not even a single depression that developed. So this is another important signal that is seen. And recently, there was a paper by Professor T.N. Krishnamurthy. He argued that basically the depressions are weakened, the counts are weakening because of enhanced CCN counts, cloud condensation nuclei, and these are basically associated with air pollution impacts over China and India. They have disrupted the organization of convection on the scale of a depression. So, so the question now we are asking is, so we see these long-term trends both in the circulation, synoptic systems as well as the rainfall. Is it a climate change signal or not? Uh, we know in the last 50 years, the temperatures, last few decades, the temperatures have increased, and basically we also know that the carbon dioxide atmosphere have been increasing during the 20th century. So the question is whether the temperature increase is due to the increasing in carbon dioxide. So recently the IPCC, the last 2-3 reports also said the same thing. The warming of the climate system is unequivocal. And since the 50s, many of the observed changes are unprecedented over decades to millennia. They also said that the warming of the increase in the global mean temperatures are by and large due to the human-induced activity, increase of the greenhouse gases in the atmosphere. And so far, the greenhouse gases like the carbon dioxide and methane and other gases like ozone and N2O, hydrocarbons, they have trapped about 3 watts per meter squared radiation because they are trapping the long wave radiation. And carbon dioxide forcing itself is about 1.66 watts per meter squared, and the non-CO2 forcing is about 1.34. So, so this has led to the increase in the temperatures, global mean temperature. So how do these modeling communities, how did they arrive at these numbers? How do they attribute that increase in CO2 have led to the warming? For this, basically, we use climate models. And when we say climate model, these are basically developed based on these are based on physical principles governing the atmospheric and ocean flows. And these laws, the physical laws, are we have the equation of momentum, horizontal momentum equations, or the Navier-Stokes equation. They are all originally developed by the well-known scientist Isaac Newton. We also have the thermodynamic energy, the equation how energy changes happen. And there is also a mass conservation equation. We have a hydrostatic balance. And we have an equation for water vapor continuity. And then on the right-hand side, you will see various terms, Q and F, and so on. These are happening on a smaller grid scale, on the subgrid scale. And so these processes have to be parameterized in model. Subgrid scale processes like clouds and rainfall and radiation and turbulence and so on, they have to be described in terms of the large scale variables. And to do this, these equations are basically all the equations of motion, the energy equation. We have to, because these are nonlinear equations and you cannot solve them analytically, so I have to discretize them. So we break the grid into the sphere into several grid points, and as you make the grid finer, the resolution increases, and then the number of computations are also will increase, and you have different layers in the atmosphere. And likewise, if you have a coupled model with oceans, you also have various vertical levels in the ocean. So typically you end up with millions of computations and you have a time step. As you make the grid size small, you have something known as the CFL criteria. The time step also gets smaller. So computationally it becomes a challenging job, and so you have to go to supercomputers or high HPCs to solve these climate models, to integrate these models. So basically you're starting with the initial state, you apply a forcing, and then you predict in time. This is the basic philosophy. And as I said, during the last century, the warming is about 0.85 to 0.9 degrees. Of course, it's not uniform everywhere. The extratropics, the warming increases are much more compared to the equatorial region. But planet as a whole has warmed by about 0.9 degrees during the last century. This is the observed temperature. So one of the immediate consequences of the increasing temperature is, as you increase the temperature, surface temperature, the water vapor, holding saturation water vapor pressure increases through what is known as the Clausius-Clapeyron equation. And you can show that for every 1 degree rise in temperature, depending on the mean temperature, background temperature, the water vapor can increase by about 6 to 10%. So immediate consequence is water vapor is going to increase. And so most models project that this is one of the extreme scenarios in the future known as the RCP 8.5. So this is an extreme warming scenario. They all project that under such scenario, because as the temperature increases, there's going to be more water vapor. So it's all going to condense and give more rainfall. So all these models are projecting that This is again from the CMIP, IPCC CMIP 5 models. So they are all projecting an increase in the monsoon rainfall. But interestingly, as I said, in the last 50 years, over the Indian region and globally, the temperatures have significantly risen. This has also been a period of warming, but the rainfall has not increased. In fact, it has decreased. So how do you rainfall over India? So how do we explain this? This is the question. So, and the circulation has weakened, the monsoon large-scale circulation has weakened. How can we explain this recent weakening? And so it cannot be purely due to greenhouse gases. And of course, models have their own limitations as well. They come with their own biases. Recently, there was a paper by Sinha et al. They argued that anthropogenically forced changes in the monsoon rainfall will be difficult to detect because there's a lot of natural variability in the system over India. They use speleotherms, which my colleague Dr. Ramesh will be presenting in the next talk. And they argued that this type of what trends which we are seeing in the last 50 years, they have also happened in the past. They have done this based on some speleotherm records. They use the isotopic analysis. And they argued that even in the past, this type of multi-decadal variations have happened. So it's a part of natural variability. So anthropogenically forced signal will be very difficult to detect. This is their argument. But there's also a different view that the other view is people have argued that aerosols, in addition to greenhouse gases, there are also various types of aerosols, anthropogenic aerosols, like sulfates and black carbon and so on. Some of them scatter the radiation, and some of them absorb the incoming solar radiation. And the net result is the radiation reaching the surface has decreased. And this can really weaken. There was a study by Chung and Ramanathan. They argued that because of the increase in the anthropogenic aerosols, they have reduced the sea surface temperature gradients in the northern Indian Ocean, and that has resulted in a weakening of the monsoon. And these are the observed trends, and this type of rainfall changes are also seen over the Sahel region and parts of the East Asian region or China. And there was another paper by Bolasina et al. They argued that basically the rainfall decreases which we see in over India in the last few decades are due to anthropogenic aerosols. Basically, the northern hemisphere emissions have increased. So the AOD, the aerosol loading has really led to introduced the interhemispheric asymmetry in the radiation balance, and which has led to the weakening of monsoon. However, interestingly, if you see this experiment, the aerosol experiment, the rainfall reduction, what they see is not just over India, they're getting all over Asia and China. Interestingly, if you see in the observations over eastern China, rainfall has actually increased. So, although they indicate that aerosol could be a forcing, there are some differences in the model simulation. Also, the precipitation decrease in the observations which you see over west coast of India is not correctly reflected in their aerosol run. So there are issues again, and but there is a kind of emerging consensus that anthropogenic aerosols have a likely role in the observed decreasing trend. Various studies have shown, and various physical mechanisms have been proposed. One is through the reduction of the solar insolation at the surface, known as solar dimming, and this can reduce the temperature gradient in the Bay of Bengal and over the northern Indian Ocean, and reduce the convective activity. And there are also view that it is not just over India, it's more of a continental scale, large scale cooling over the northern hemisphere by the sulfate type of aerosols, and which can weaken the monsoon. This was by Bollasima. And there's also a paper by Ganguly et al. Who argued that aerosols, they try to decrease not just the surface temperature gradient, but also the tropospheric temperature gradient, and weaken the vertical shear of the monsoon. And interestingly, some of the aerosols like black carbon, which are trapped in the first few kilometers, first 2 to 3 kilometers above the boundary layer, because they absorb the solar radiation, so they warm the layers above the boundary layer, whereas below the surface the temperatures are reduced. This leads to what is known as an increase in the static stability, and the increase of static stability by solar absorption can weaken the circulation. And there is also a reduction in the temperature at the surface cooling. And also when you cool the surface, it can also lead to decrease of water vapor availability. So various mechanisms have been proposed. And so on the one hand, we have the GHGs which are trying to increase the temperature, increase the water vapor holding capacity and lead to more rainfall. On the other hand, the aerosols are trying to compensate it by trying to bring down the solar radiation at the surface and trying to reduce the rainfall. So there is a kind of tug of war between these different forcing elements, between the greenhouse gases, aerosols and other changes. So we did this experiment study which was later on reported in Nature News and Views. And I will be basically talking about this, how do we decipher the desiccation trend of the monsoon rainfall in a warming world. So what we did was we basically used a global model. The interesting, although it's a global model, over India, over South Asia and even a wider region, we applied a very high resolution zooming. So the grid is not uniform. Over this zoomed region, the grid size is much smaller. It has a high resolution of about 35 kilometers. And as you go away, the resolution gets coarser. So the advantage of having this zooming is you will be better able to resolve the orographic effects, also the regional forcing like the aerosols and the land use changes that have happened. And and interestingly, this model, the global rainfall distribution as well as the global monsoon circulation as well as the regional scale features are much better resolved when you have this zooming. So the zoomed version shows much more rainfall over India as compared to the no zoom run, which was a 1 degree by 1 degree or 100 kilometer by 100 kilometer, which is relatively drier. This is a mean monsoon rainfall. The zoomed one, the rainfall distribution, you can see the improved rainfall along the Western Ghats and Northeast India and also over the Indo-Gangetic Plain. The top one is the observation. And interestingly, when you improve the rainfall simulation, the Somali jet or what you see over the Arabian Sea, that also intensifies. So it is telling that basically the precipitation and wind, they are constantly interacting. So this is one of the good models. And we said that why not use this model to make some climate projections and also try to look at what has happened in the historical period during the 20th century. So we had two experiments. One is the historical run, which includes natural forcing. By natural, I mean solar irradiance changes at the top of the atmosphere, volcanic changes, and anthropogenic forcing due to greenhouse gases like carbon dioxide, aerosols, different types of aerosols, land cover changes. And this was a 120-year run. It took us a lot of time, more than 2 years to complete this run at this very high resolution. And we also have a experiment with only natural forcing. There are no anthropogenic forcing. So if you this is known as the historical natural. So by comparing the historical and the historical natural runs, you will be able to understand how much the anthropogenic influences have affected the monsoon. And we also make a future projection following one of the scenarios known as a RCP 4.5, which is a kind of moderate scenario where the radiative forcing at the top of the atmosphere reaches about 4.5 watts per meter squared by end of 21st century. And all these runs were made using the LMDZ model, which I discussed earlier. And these are basically atmospheric model runs where the sea surface temperature, which is used to force these models, came from the coupled model run, the original IPSL coupled model. And we also had a run only with greenhouse gases. So there was no aerosols and land use change, only GHG forcing. Like carbon dioxide. And what we see is when you compare the surface temperature simulation in the historical run and then the future is continuing RCP 4.5, the yellow is the natural line. You can see the warming temperatures clearly attributable to this, a very significant warming that has taken place in the 20th century. You can associate with the anthropogenic influence. And you also see those warming trends over India and which is projected to increase in the future over South Asia. But interestingly, when you look at the rainfall during the June, July, August, September season, what you will find is this black line is the observation from IMD data set. You can see a decreasing trend in the rainfall. This is the Pai et al. IMD data set, which is about 7% decrease. Our historical run is the brown line, which is also showing a decreasing trend. But you don't see a decreasing trend in the historical natural experiment, that is the blue line, which is showing this decadal and multi-decadal variability, but there is no clear trend. And what is also interesting is the rainfall is projected to decrease. We had only one realization in the 21st century, at least in the first half of the 20th century. The advantage of using the high resolution model is the mean rainfall is somewhat very closer to observations. But if you look at all the IPCC models, the CMIP-5 models, the mean is nowhere close to that. It is far, far underestimated because of the coarse resolution. And there is a lot of spread among these models. There are about 35-40 models. There is a lot of spread. And in fact, it shows a slight increasing trend in the mean rainfall over India, as I told, because of the increased water holding capacity. So interesting, what the point is I want to say is the historical simulation captures this decreasing trend, although it is somewhat more exaggerated in the model. And the other thing is the use of high resolution. We counted the heavy rainfall events from the daily rainfall over central India, same region of Goswami. We see that just like the observations, the historical run shows that the increase in the heavy rainfall, whereas the mean rainfall is itself decreasing, and it is further projected to increase in the future, but you don't see those in the natural run. And we have tried different convection schemes to see whether this is a robust result. Is it sensitive? We see that no matter you change the choice of the cumulus convection for representing clouds, whether it's two different, we do see a decreasing trend, which you don't get it in the historical natural using the same convection schemes. And whereas the frequency of heavy rainfall increases irrespective of the choice of the convection. And when we look at, this is the attribution we did, you take the difference between the historical minus the natural for the last 50 years, you can see all these red areas with the dots, which is basically a statistically significant areas along the Western Ghats, along the Indo-Gangetic Plain, a decreasing trend in the rainfall, accompanied by a weakening of the monsoon flow. You can see an anomaly, easterly anomaly, indicating that the southwesterly flow has weakened. And you also see interesting changes, consistent changes over Sahel and over China. And over Eastern Indian Ocean, over the equatorial Eastern Indian Ocean, precipitation has increased, actually increased, shows an increase in this experiment, which I will come. But when you do only a GHG forcing experiment, only with greenhouse gases, without any anthropogenic aerosols and land use change, the rainfall actually intensifies and the circulation strengthens. So we rule out the possibility that this decline is because of the greenhouse gases. It is because due to the other regional elements like the aerosols and the land use change. And during the last couple of centuries, significant land use changes have happened over South and Southeast Asia. About 40 to 45%, there are publications telling that about 40 to 45% of forest cover has been replaced by agricultural land during the 18th and the 19th centuries. And it has also continued in the later part. And these publications are there. And these data sets have gone into the forcing. The other thing is the anthropogenic aerosols, both the scattering and the absorbing type. So there is a reduction in the radiative forcing due to the aerosol at the top of the atmosphere. And there's an increased absorption. You can see over Indo-Gangetic Plain and over China because of a lot of pollutants. And the other important signal is there is a very strong pronounced warming of the equatorial Indian Ocean. It has warmed by about 0.5 to 1 degree in the last 50 years or so. So these are all important signals. So on the one hand, what we are finding is because of the increase in the crop fraction as compared to the tree fraction, the planetary albedo in the model simulation has increased by about 9 to 10%, that is shown in the green line, just over India. And whereas the warming of the equatorial Indian Ocean has happened by about 0.5 to 1 degrees, and the anthropogenic aerosols have largely dominated the Asian region, the South Asian region, since the 60s and the 70s. So because of the increased albedo, you are losing a lot of radiation back into space. So that has to be compensated by increased subsidence. So we find in the simulation that sea level pressure increases over India, both in the model and the observations. But because of the increase in the temperature, the water vapor itself has increased over model, in the simulation, and projected to increase. But there is a lot of subsidence happening over India. And since the monsoon has weakened, when you look at the winds at the lower level and the upper level, you have a strong shear. in the upper level you have strong easterlies, winds coming from the east. So this shear is a measure of the intensity of the circulation, monsoon circulation. That shear, easterly shear, has actually weakened. So as the rains decrease over India and as the temperatures are increasing, we find that there is a decrease in the soil moisture in the model simulation, which is projected to continue into the future. So because of the warming associated over the equatorial region, associated with sea surface temperature, there is more convection, more upward motions over the equatorial region, which is trying to produce descent over the Indian landmass. So basically the monsoon overturning Hadley type of circulation has weakened and is also projected to weaken in the future. And so we are seeing the response to the aerosols, the land use change, the SST warming, they're weakening the overturning circulation. But once you decrease the rainfall over India and weaken the convection, much of the circulation in the subtropics and the extratropics, which are associated with the cold westerlies, they try to intrude southward and they can produce very large scale continental scale patterns. You can see that there is a large scale cooling of the troposphere in response to the weakening of the convection over the Indian region. So you have warmer temperatures in the equatorial region and cooler temperatures in the troposphere over the high latitudes. So these are all various feedbacks that are happening. So the main result what we find is when you compare only the greenhouse gas experiment and the historical experiment having the land use and the aerosols, what we find in the greenhouse GHG only experiment, both the moderate rainfall events over central India, 5 to 100 millimeter per day, as well as the more than 100 millimeter per day, those type of events, they tend to increase. You can see this is all relative to the historical natural experiment. Whereas in the historical experiment, we find that the heavy rainfall events, more than 100, they have increased at the expense of the decrease in the moderate rainfall events. So these two categories are very distinctly different. And this is telling the importance of the non-GHG forcing elements. So basically what I want to summarize is, we have looked at the long-term climate change. We did some modeling experiments using a high-resolution model, looking at the monsoon precipitation changes during the decreasing trend in the monsoon rainfall and the increase in the heavy rainfall event occurrences. And we are attributing this to regional forcing, the aerosols, land use change, and the equatorial Indian warming. And because of the use of the high resolution, it's a big, all the second order moments are better captured. A robust increase in the frequency of heavy rainfall occurrence are seen in the climate change simulation. And the role of aerosols in the weakening of monsoon, now there's an emerging consensus from different groups. Of course, the monsoon has a strong internal variability over the South Asian region. So it is necessary to have multiple realizations to better quantify the aerosol impact on precipitation. We could not separate the effect of aerosol and land use change, which we are trying. The Indian Ocean warming signal, this problem is not well understood. Our own impression is that my colleague, Dr. Roxy Matthew at IITM, he has also shown how this Indian Ocean warming can weaken the land-sea contrast and it can have an impact on the monsoon. But weakening of the monsoon circulation itself can reduce the upwelling in the equatorial Indian Ocean, large part of the Indian Ocean, which is coolest during the summer monsoon time. And that can contribute to this warming. So it's still an open problem and that needs further studies. And we have used basically a standalone atmospheric model, but we will need a coupled model to better comprehend the aerosol forcing on the South Asian monsoon. So what is the way forward? At IITM, we have developed an Earth system model, a fully coupled model. It's not just atmosphere, ocean. It has an interactive cryosphere and a biosphere. And we will be participating in, and this model we have also improved the radiation balance, this global mean temperature. And the latest version, the ESM2, the monsoon rainfall over India has significantly improved because of the use of a new convection scheme. And it also captures many of these disturbances that form in the Bay of Bengal, synoptic scale disturbances. So we have started the CMIP runs, and this model will be contributing to the IPCC, the first from India. So we want to look at this problem, and we have also introduced aerosols in the model. We will be looking at all these aspects in this model. And with this, I want to end my talk. Thank you very much.
there any question from audience side?
Hello. So the question which I have essentially a query. So the aerosol increase and the land use are non-uniformly distributed across India,
Correct.
as I would imagine.
Yes.
So how that impact on a more macroscopic level? Because the changes are on a more microscopic and inhomogeneously distributed across India.
Yeah.
So how do we relate that?
Yeah. So basically what, the distribution is not uniform, but what we see is when you look at the radiative forcing simulated by the aerosols, you can see that the forcing at the top of the atmosphere is dominant over regions where you have higher emissions. And you can see in the atmosphere, basically this is all in the boundary layer and above, there is a lot of absorption. So these are indicating more of absorbing type of aerosols, which tries to decrease the static stability. So we cannot really go down to at a very microscopic level. So we are really talking about the changes in the forcing on a scale of a continent or a subcontinent. So it is on that scale we are talking. So because if you want to really influence the circulation, the monsoon circulation, the large scale, the anomaly, the forcing has to operate on a much larger scale. Then only you can impact the circulation and then influence the precipitation. Okay. Yeah, thank you very much. So now I have the job of convening. So it's a pleasure to welcome Professor Ramesh from PRL. He is a very well-known scientist and he's a very accomplished scientist, and I was in PRL and he's in fact my senior, and I know his capabilities are fantastic and his scientific contributions are enormous. He has published more than 200 papers and he has worked in various aspects of climate sciences. He has received various recognitions like the Indian National Science Academy Young Scientist Medal, the Shanti Swarup Bhatnagar Award, the Third World Academy Prize for Earth Science in 2006, the Nobel Peace Prize for the IPCC report fourth report in 2007, the Ramanathan Gold Medal 2011, ISRO Lifetime Achievement Award, and he is a fellow of the Indian National Science Academy, the Indian Academy of Sciences, the National Academy of Science, and the Third World Academy of Sciences and the Geological Society of India. So we are really honored to have Professor Ramesh, and we look forward to your talk. Thank you.
You have color mic or?
I can provide you in a second. So you have power now?
Color mic, please give me color mic. Good morning. To address important questions in science, you should have some data. And if you look at the IMD data on monsoons, it goes goes back by about 100 years. That's not quite enough, because you look through a window, the window is small, your scenery is also small, but if your window is bigger, you can look at a larger scenery. So this window of 100 years through which we look at the past has to be expanded. So what we do is we look at natural archives which preserve information about monsoon changes in the past. So this is my talk is about looking at the past and how do we infer monsoon changes over India over thousands of years. So the advantage is we come to see things which we don't see in the last 100-year cycle. For example, the previous speaker mentioned the desiccation happening for the last 50 years or so. Now looking at some archives like tree rings in Nepal, Himalaya and all the other parts of Himalaya, we see that this desiccation is not only 50 years, it goes back to about 200 years. There is a slow change which has been happening. So these are the things which one comes to know by looking at changes in the past. So I will give some overview of what we have learnt in addition to what we already know from the published literature. So, it is important to, when you go back in time, for example, the best way to measure monsoon rainfall is to put a rain gauge and measure every day how much rain is collected. That is the most precise way. But if you go to thousands of years back in time, you have to rely on indirect methods. So, the proper calibration is important, and we use oxygen isotopes, which is this is delta 18O. I will explain what this is. So, we measure oxygen isotopes and we use this as proxy for monsoon rainfall, and I will discuss some new results on past monsoons. New results on past based on tree ring chronologies. Trees have annual rings, and these annual rings you can measure the oxygen isotope and reconstruct how the past rainfall has changed, monsoon has changed. And then you have ocean sediments, you have the fossils in the ocean sediments which have recorded the oxygen isotope change in the sea, which relates to the monsoon. And then of course cave deposits like speleotherms, they are called stalactites and stalagmites, which also preserve the oxygen isotopic composition of past rainfall. And then we ask some science questions and the conclusion. This is the plan of my talk. Before we go into the talk, some definitions. Holocene refers to a geological period which is roughly last 10,000 years. So, most of my talk I will concentrate on the last 10,000 years, how the monsoon has changed. Speleotherm refers to a cave deposit. It can be a stalactite or stalagmite which grows in caves. I will show some pictures later on during the talk. What is a monsoon proxy? A monsoon proxy is something that preserves the signal of monsoon. It can be either a wind proxy or a rain proxy. It can be a proxy for past monsoon rainfall or wind intensity. So, these are the two things which we look at. And the oxygen isotopic ratio is defined as the abundance of oxygen 18 to oxygen 16. So, oxygen has 3 stable isotopes. They are not radioactive isotopes, they are stable isotopes. They do not decay. Oxygen 18, for example, in the water bottle kept here, it is all H216O. Normally, most of it is made of 16O, but about 0.2% of it is 18O. Small amount of oxygen 18 is there present naturally. And the amount of oxygen 18 present naturally in different things change with processes. For example, when there is evaporation from the ocean, H218O being slightly massive, it does not evaporate at the same rate as H216O. So, the clouds when they form from the sea, the clouds will have more of the lighter isotope H216O compared to the heavier isotopes. And then the clouds come over land and then they precipitate. So, the oxygen isotopic composition of sample to sample varies because of the physicochemical processes which take place. So, whenever there is a physical process like evaporation or condensation, or there is a chemical reaction, the isotopic composition changes, and these isotopic compositions can be measured using a mass spectrometer very precisely, and this can be used to reconstruct past monsoon variations. So, this oxygen isotopic composition is measured as in per mil units. All of you know percent, one dot, slash and one dot, that is percent. Here if you see there is a symbol and the lowermost end of this thing, this is called per mil. This is parts per thousand. So, it's percent means out of 100, per mil means out of 1000, because these numbers are small, we use per mil symbol. So, let us go to when you want to look at the past, you have to go to a place where the signal is very strong. The monsoon signal is very strong in 2 places. For example, in the Western Arabian Sea during the monsoon, Dr. Krishnan showed a lot of wind trajectories. This is a very big jet there called Findlater jet, and that causes a lot of upwelling in the ocean. So, this part, Western Arabian Sea, this part gets a lot of upwelling during the monsoon, and the surface temperature, sea surface temperature reduces to about 4 degrees. That causes a very significant monsoon signal. So, if you look at people, what they have looked at, when you want to look at the monsoon radiation for the last several thousand years, millions of years, people have go to such places where the signal is very strong. So, what is the signal they look for? Normally in the ocean, there are organisms living, they prefer certain temperatures. Some species prefer to live in warm temperatures, some species prefer to live in cold temperatures. So, those species of animals or these fossils which we get, if there are cold living species, for example, some polar species which are living only in cold regions, whenever such upwelling and cooling is there, they prefer to come in the tropics. So, one such species is G. bouloides. I will show you a picture later on. G. bouloides is a foraminifera which secretes calcium carbonate. Size is about 400 microns, small shell which is made, and that grows here abundantly. That is interpreted as the indicator of past upwelling. So, when people count the number of these G. bouloides, they interpret it as upwelling intensity. So, higher the abundance of these particular species, higher the upwelling, therefore, the monsoon is interpreted to be very strong. Whereas, when you come to India, you can see on the western side, Western Ghats, Krishnan also showed a picture of modern day monsoon. He showed an average picture. If you see a blue, if you remember his slide, there were two big blue patches in the over the Indian map. One is the Western Ghats, another the northeast. These are the places where you get very high rainfall during the monsoon season. So, on Mangalore, this region gets about 400 millimeters of rain, whereas the average, all India average about 1000 millimeters. This is 4000 millimeters rainfall here. So, that runs off into the sea, and the salinity reduces significantly in the coastal region. Whenever there is runoff is higher, the salinity is lower. That is the signal. Now, unlike in the Western Arabian Sea where there is no calibration, it is only a qualitative indicator, the abundance of the species. Here we have a quantitative calibration. This is the calibration which you see, x-axis salinity, y-axis the oxygen isotopic composition of the surface water. Whenever the salinity is high, that is no runoff, no monsoon, poor condition, drought means the salinity will increase. The fresh water supply is cut off, salinity will increase, the oxygen isotope also increases. Whereas, when the monsoon is strong, it comes toward this direction, salinity decreases in the coastal region because of runoff, salinity decreases, and oxygen isotopic composition also decreases. So, there is a good calibration in the Western Arabian Sea in the oxygen isotopic composition of surface water and salinity. The same thing is preserved in the sediment cores also. When you collect sediment cores, say for example, when you go from south here all the way up to north and collect sediment cores, you see the precipitation is quite high in this region. As you go towards Gujarat and desert regions, the precipitation is small. So, you will get low salinity here and high salinity here. This is also preserved in the fossils, oxygen isotopic composition of the fossils. So, we have a very strong calibration to interpret the changes during the last 10,000 years, and we see the monsoon has been increasing steadily. This is precipitation minus evaporation in millimeters. So, the monsoon has been steadily increasing during the last 10,000 years. This we published long time ago, 16 years ago in EPSL. But 3 years later, Gupta et al. Published a paper which said that the monsoon intensity, the wind intensity has decreased because the G. bouloides abundance has decreased during the 10,000 years. So, these two are the contrasting things. So, the question to be asked is, when we see the runoff has been increasing continuously in the Eastern Arabian Sea due to increasing monsoon, the Western Arabian Sea signal sees that the monsoon intensity has been weakening over the last 10,000 years. So, this is a question to be addressed. So, we address this question using various proxies. Here the same thing is shown here. This is a speleothem record from the Arabian Peninsula. This is the Gupta records of G. bouloides abundance, and this is some plant wax from the Arabian Sea. These three records show very clearly that the monsoon has been decreasing in the last 10,000 years. Now, we look at speleothems. Speleothems form in caves. There is a rainfall and the soil is rich in carbon dioxide because of plant respiration. The water, when dissolved in carbon dioxide dissolves in water, it becomes acidic, it dissolves the calcium carbonate, which is the limestone here, and when the water slowly drips, you form calcium carbonate. And the oxygen isotopic composition of this calcium carbonate gives you the oxygen isotopic composition of the rainfall which occurred over the surface. That is the assumption. And you see a man standing here. These are speleothems. These are the cave deposits. They are called stalagmites, and these are called stalactites. And they can go back to thousands of years, millions of years. They can be precisely dated using uranium thorium isotopes. So, how do we interpret the oxygen isotopes? The oxygen isotopic composition of rainfall is negatively related to the amount of monsoon rain in a negative way. That means, for every 100 millimeter increase of monthly rainfall, the isotopic composition reduces by about 1.5 per mil, whereas the experimental accuracy with which we can measure is only 0.1 per mil. So, very precisely we can measure. Throughout the tropics, the International Atomic Energy Agency has measured all these places. People have measured the isotopic composition of rainfall, and it also shows a nice negative correlation. So, this is the correlation which we use to convert the oxygen isotopic composition of speleothem to the amount of rainfall. Now, it is important that the calibration proxy is properly calibrated, so we get accurate idea about how the monsoon changed in the past. One problem is that isotopic rainfall measurements are available for 100 years mainly in metros, but if you want isotopic composition, it is not available. Isotopic composition is available in very few places over India. So, what we do is we run what are known as isotope enabled general circulation model, just like Dr. Krishnan showed you results from general circulation models. There are models which we can also, in addition to simulating the precipitation amount, they can also simulate the oxygen isotopic composition at various places. So, there is a batch of models called stable water isotope intercomparison group 2 models, 10 models, and we compared these to 10 models. So, this is the region which we look at, the core monsoon region defined by Goswami, which was also shown by earlier speaker. And this is how these different models, all these model names are given here, and this is how the monsoon simulated. You can see large variations in the actual, though all of them produce precipitation during the monsoon season, the amount of rainfall and the season wise variation is quietly different. This can be easily seen on this right hand side. What you see is what is in a Taylor diagram. Taylor diagram has standard deviation of the model in this axis, and the correlation is plotted here. So, any model is good which has low standard deviation and high correlation. Correlation is high, whereas standard deviation is low. That is a good model. So, you can see some models have been nudged runs, they show very good correlation. Some models show very poor correlation. Now, if you look at the multi-model comparison of spatial pattern of rainfall, many of them are not able to really predict, because these are the CMAP and these are the actual measurements, whereas if you see the standard deviation and correlation coefficients are different for the simulation of spatial pattern, and for oxygen isotopic composition also it is quite poor. So, this is the interannual variations. Interannual variations, some models are able to produce very good results. So, the question we are asking is how much is the correlation between the oxygen isotopic composition of rainfall and the monthly mean as recorded by these models wherever caves are present. I am showing Mamluk cave, Akalgavi cave, Dandak and Baratang caves. These are the caves located various places which we have been studying, and in all these cave locations is there a relation between oxygen isotope and the June, July, August mean, summer mean? Yes, because this negative correlation is the red patch. You can see red patches everywhere. So, there seems to be the models are able to simulate this oxygen isotopic composition. In addition, the global network for isotopes in precipitation, GNIP data, when we look at this region which gets northeast monsoon rainfall more than the southwest monsoon, they are very sensitive, and there the amount effect is very, very significant. So, if there are caves in Sri Lanka and this part of the India, they are best suited for reconstructing monsoon rainfall. Now, this is about speleothems. This is an introduction where we look at only the calibration of the proxy. The actual results from speleothems I will be showing toward the end of my lecture. Now, tree ring chronologies have been constructed, new tree ring chronologies, and for example, Sano et al., who worked with me, we showed that the Holocene last 220 years Nepal Himalaya monsoon has declined. So, this is published in one of the journals called Dendrochronologia, which is specialist journal for people studying tree rings and climate, Dendrochronologia, and we have shown based on one particular site in Nepal that in the Nepal Himalayas during the last 220 years monsoon has been steadily declining. Now, what we have done is we have increased the number of sampling sites. So, in all this paleoclimate, one thing one should remember, this all labor intensive. You have to go to the field, collect samples, make analysis. This takes years and years. It cannot be quickly produced. Similarly, cave deposits, you have to go to the caves, explore, bring them, date them, and only after dating them you know whether they are falling in the Holocene or they are millions of years old. Then you have to go back, and this is all done by trial and error, because in the field you don't know what is the age of the sample you are collecting. So over a period of years, 10 years of hard work, we have collected samples all over the Himalaya, 1, 2, 3, 4, 5, 6 places we have developed. We are not only looking at the ring width, we are measuring the oxygen isotopy composition, which is a more precise measurement of, gives a measurement of rainfall. Using these are the chronologies, I will skip all these details. The oxygen isotopy composition is very highly correlated with the monsoon rainfall, and this is the place. Long-term correlation is quite negative. See, the oxygen isotope is negatively correlated with the amount of rainfall. This is the amount effect, and these are the correlation coefficients. I will skip all these things. I am going forward. And if you look at the stalagmite results from northern India and tree ring record, there seems to be some similarity, but they are different proxies, one should remember. This is an important curve. People showed that the land sea temperature contrast has been decreasing. So the blue one is the Indian Ocean SST. Indian Ocean is warming, as Krishnan pointed out earlier, and the Tibetan plateau temperature is not warming so much. So the land sea temperature contrast has been decreasing. This was also shown by Roxy et al. As mentioned by Krishnan. So the land sea temperature contrast is reducing the last 200 years. This is also Roxy et al.'s paper, which they showed very clearly that the SST in the Indian Ocean has been increasing. The precipitation over central India is decreasing. This they attributed to the reduction in the land sea temperature contrast, but there are issues with this, as Krishnan has mentioned. There are other issues which has to be, it's still an open problem, but this is true as far as data is concerned. And what we have done using this training data is to show that this has been there, this declining trend is there for the last 200 years, it is there. So this is the result. This result is red curve, H5 regional tree ring. Using the Himalayan tree ring signals, whatever we say, this land sea temperature contrast is highly correlated with tree ring oxygen isotopic chronology. So whenever the oxygen isotopic composition is increasing, that means there is a reduction in the monsoon. So this reduction is not only restricted to last 50 years, which you see very clearly, but it is a slow cycle which has been happening for the last 200 years. So what we found in Nepal Himalaya based on one particular site has been replicated over the entire Himalaya, mostly using 5-6 different sites. We have replicated this, and we now have very solid evidence that over the Himalayan region also, not only in central India, in the Himalayan region also the monsoon is declining for the last 200 years. And then the ocean sediments, now more measurements are available from Deshpande et al. And other people who have looked at the oxygen isotopic composition in the ocean, and we are able to in a better represent these things. And when we look at the many ocean sediments, for example, if you go here, this curve shows you the many ocean sediments have been measured. In 2000, we published, I showed you earlier on, in 2000 we published a paper based on a core of Mangalore that the monsoon rainfall has been increasing, not decreasing, over the last 10,000 years. Now many other people have done cores all over the place, from equatorial Indian Ocean all the way up to north, so many cores. If you look at the results of all these independent workers, all of them show during the Holocene the oxygen isotopic composition has decreased. That means the rainfall has been increasing. Monsoon rainfall has significantly increased. All of them show. So the conclusion is based on both land evidence and evidence from the Eastern Arabian Sea, the paleoclimate data very clearly show that during the Holocene monsoon has not declined. Monsoon has only increased. Rainfall has only increased during the last 10,000 years. Now we go to speleothems. We have analyzed many speleothems. These are the back trajectory calculations. This is a cave called Belem cave, and this is the back trajectory analysis. So all of them get rain from this region. This is how a sample looks like. You have bands, and these bands are dated using uranium thorium, and we have now a data set for the last 10,000 years. During the 10,000 years, you see the oxygen isotopic composition has not significantly enriched. It is more or less stable. In the early stages, there was an increase in monsoon, and there was a small decrease, but overall trend, if you see in the last 6,000 years, there is no change. I mean, it is not going to, it is not declining. There is no declining trend as mentioned by Gupta et al. And others. So, we have now solid evidence to show that the monsoon rainfall, if at all, has increased slightly, but it has not decreased during the last 10,000 years. So, what are the questions we are asking? Science question. People earlier attributed that this curve, this dotted curve which you see here is the insolation, incoming solar radiation. They say incoming solar radiation has been declining during the Holocene, and therefore the monsoon intensity has also declined. But whereas we don't see one-to-one correlation between the solar insolation and the monsoon. So, this is different things, they are not related, and we have also done some proxy comparisons between different places, and there seem to be evidence for the little ice age reduction in rainfall and medieval warm period increase in rainfall are also seen in this thing. So, I would like to conclude my talk. We have gained understanding on interpreting the oxygen isotopic composition, because any paleoclimate system has to have a proper calibration, and one has to spend lot of time to improve the calibration. That is what we have done using GCM models. There is a clear evidence for decline in monsoon rainfall over the Himalaya during the last 2 centuries. Eastern Arabian Sea sediments confirm that there was no strong decline in monsoon over the Holocene. The Indian summer monsoon reconstruction based on 3 stalagmite samples show rapid increase in monsoon during early Holocene, and although solar insolation plays a major role, whatever millennial scale, centennial changes cannot be explained using these internal forcings. So, these are some results which I shared with you. So, I would like to thank the organizers of Indian Science Congress, especially Dr. D. Narayan Rao for inviting me for giving this talk, and I would also like to thank collaborators who helped me in building up these networks, and this program was funded by ISRO GBP. Thank you.
We have time for a couple of questions.
Sir, will you please show that foraminifer Jabrolite? You told that foraminifer, some foraminifer you wanted to show. Can you show it?
Oh, I forgot, yeah. I don't see any picture in this. I don't think I have put any picture in this. No, I have removed that picture. I don't have that picture. I don't have, sorry.
So, yeah, just a minute.
What is the best resolution you can get? Can you get a decadal scale type oscillation or a yearly or a seasonal type oscillation?
I didn't follow what your question is.
Can we get a decadal type oscillation in your paleoclimate, or maybe yearly, or
Yeah,
maybe
for
seasonal?
example, if you look at the tree rings, they have a resolution of 1 year, so you can easily get a decadal type oscillation. But if you go to ocean sediments and speleotherms, they don't have even decadal resolution. So decadal oscillations you cannot get. Multi-decadal and millennial scale oscillations you can get. Decadal oscillations you can get only in tree rings. Yeah.
Okay, thank you.
Any further questions? Professor Ramesh, I want to ask.
Yeah.
So that the Nepal tree ring you showed that it is indicating a. So, but do we have rainfall data in that region?
No, we don't have rainfall data. We don't have rainfall data. What we have done is, whatever data we have, we calibrate it with respect to whatever existing data is there.
Okay.
So if you look at the original paper, it gives you the calibration. So if you look at this picture, for example, in the bottom you have the bottom curve, you have 1950 to 2000.
Okay.
That is the calibration.
Okay.
You can see the black one is the tree ring, and the red one is the monsoon index. These are two correlated.
Oh, that's a
And
very
on the top calibration is all India rainfall.
Okay.
The blue one, the red one is all India rainfall, and black is the oxygen isotopic composition of tree ring measured in Nepal. So based on this correlation, we reconstruct, go back to 220, 300 years. So that is the base of correlation. Yeah. We don't have data,
Yeah.
but whatever
But some 50 years you have some.
50 years we have the New Delhi data.
Okay.
Yeah. That's all it is there. It is not there. It is not perfect because oxygen isotopic data for a long time you don't have. So what we have done here is we have not done, we have calibrated with the monsoon amount of monsoon rainfall with the oxygen isotopic composition of the tree ring. That we use the calibration for reconstructing the past.
Thank you. Thank you.
So now I request our convener, Dr. Krishnan, to present a memento to Professor Ramesh.
Should I come down? Yes. Yeah. So such a big memento. Thank you so much. Okay, thank you. Success baggage. Thank you. Thank you. Sorry, I couldn't come up. Yeah.
So now I request Dr. M.R. Ramesh Kumar, Chief
There a cover
Scientist
for
at National Institute of Oceanography,
Cover.
to present a memento to our convener, Dr. Krishnan. Thank you. Yeah, so
Two speakers, also Professor Ramesh, for a brilliant talk, and thank you all of you. Thank you.
So now it's a break, and at 12 o'clock we have another session called Blue Economy.
Where is it? I mean, sorry, I should remove this one. Where is the tea break? We can get the tea coffee there now.
Tea coffee there. BAP place is slightly far away from here. That's what I'm suggesting.
No problem, no problem.
Have you collected your
Mobile phone.
mobile phone collected? Yes, sir.
Next session, my name is Atmananda. India, are you off here?
Told him to cut the mic, but he's doing the other thing. It's okay, sir. Sir, 1 second, sir. I'll just create a folder. Sir, your name, sir?
Atmananda. Atmananda.
You are the first speaker.
But I think some change is there.
Oh,
That the last person wants to speak first. But anyway, you load it.
I've known that.
You can only switch on one at a time. You both cannot switch on together because when the speaker is speaking, there is no voice, then you have to use one voice at a time.
And presentations will be deleted right after your talk.
So both have to. One person gave a number, right? Just speak near.
No, nobody gave any number. Nothing like this. I didn't get anything, sir. Sorry. Sir, I just write your name. Oh yes. Hello. Correct. Namaskar. Sir, I cannot give presentation without any permission from him. If you get permission from him, I can.
You
give.
ask Krishnan. He may give. This is a published material. You can just ask him.
Okay. The problem is I am unable to
No,
give.
no, I know. You are not authorized to do that.
So,
In fact, he has deleted, I think.
I will delete right away after the session. I will delete because I don't want to store any of the information. Because the first
You are copied, no?
I copied.
Copied. Just see whether it is working.
This is the
No,
presentation.
just put it online. No?
Hello. No. You can check from.
But it doesn't come
No,
sometimes.
it doesn't come. It's better to check there.
I'll ask her.
Hello.
Anna. No, that guy, the guy with the cap.
LED. Presentation LED. Presentation LED. Yes, sir, you can check it now. No, good.
Sir, it is ready. Sir. This one. Sir, in case if you want to point something, you can always do this. The cursor is this. Chandramohan, just to leave the photography to somebody else because you are taking care of this one. You check the biography, everything correct. Ask
Check it.
Kamala Bharati.
He's one speaker.
He's the first speaker.
I may not be first because Tiwari wants to speak first.
Okay. His name
His name is Atmanand.
Atmanand. Sir, we want to check the biography before the
Yes,
talk.
yes.
Just want to make sure that
No,
everything.
no problem. Shanai only is going to introduce, no?
Okay.
He knows me. We know very well.
Oh,
so
Sir,
no.
just have a look at least in case because sometimes you have to give it to the press or something. So just to see if everything is fine. Or if you want to add something, you can. Okay, thank you. You can
Thanks.
take it. You can take it.
Sir, if you need any help, you can ask one of us.
They are coming. Actually, Shanai who is going to chair is. He has finished darshan. He is coming. They are on the way. So.
So anywhere, still 1 hour.
Yes. So he will come. Rajan also is coming.
Please have a seat, sir.
Tiwari, I don't know who is the person. You have to ask. I mean, he may come and give us.
Yeah, sure.
So one speaker is okay. You pick that one. Oh, it is not that. I don't have any numbers, anything. I don't know what to use for this report.
No, he said if we call, he will bring in 15 minutes.
Shani, he says convener is Rajiv. Oh, okay. So probably you need to invite. There will be a problem with the Shani convener. So this guy is going to be the convener. Oh my God. So why? I don't know. Just he said that. I don't think so. So you check Shani. You study Shani. Who is Shani? Satish is Shani, director. Engine. Shani. He is not around now. You at least read his profile. You read his profile. we had to check before.